Hello and welcome to Into the Abyss podcast. My name is Todd Decker. I'd like to start things off with a joke, a math joke. An infinite number of mathematicians walk into a bar. The first orders a beer, the second orders half a beer, the third orders a quarter of a beer, and so on. After the seventh order, the bartender pours 2 beers and says, "You fellows ought to know your limits." Okay, I tried to start things off in a cute way. Anyway, the joke is that if they keep following that pattern to infinity, the total approaches the equivalent of 2 beers. That is the limit of the series. In mathematical terms, this is an infinite series. An infinite series is a sum of infinite terms. And in this joke, the series is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on out to infinity equals 2. Each term in the series is half the previous term. And if you continue this out to infinity, whatever that means, it ends up adding to 2. Infinite series can be either convergent or divergent. The series just mentioned is convergent because it adds up to a finite number. But others end up blowing up to infinity, and those are divergent. Convergent series fascinate me. Their aesthetics remind me of Cyclopean masonry, famous among the Inca, where all the stone pieces fit together perfectly as if part of a single block. These series reveal infinite structure within numbers. I'd like to share some of my favorite examples of infinite series. The previously mentioned series, adding up to 2, is interesting. It shows infinite structure within this simple integer, 2. But I'm especially interested in infinite series for irrational numbers. Irrational numbers like pi, e, and logarithms have infinite non-repeating decimal places. How can we find the values for all these digits? This is where infinite series become especially useful. Pi, approximately 3.14159, is the ratio of circumference to diameter. How can we find its value? Maybe make a really big circle and keep on making measurements with more and more accurate tape measures. No, that won't go very far. Fortunately, there are infinite series that add up to pi, or ratios of pi. And what's fascinating is that these series seem to have no obvious relation to circles, diameters, or circumferences. Here are some of those series. 1 divided by 1 squared plus 1 divided by 2 squared plus 1 divided by 3 squared plus 1 divided by 4 squared, and so on, is equal to pi squared divided by 6. Or another one, 1 divided by 1 minus 1 divided by 3 plus 1 divided by 5 minus 1 divided by 7 plus 1 divided by 9, and so forth, is equal to pi divided by 4. You look at something like that and wonder, what on earth is pi doing there? Where did that come from? Irrational numbers by definition cannot be expressed as fractions, but they can be expressed as infinite sums of fractions. You can get an irrational number like pi just by adding up these simple fractions, at least by adding up an infinite number of them. Of course, we can't actually do that, but we can still add up many, many terms. And with computers, we can add up millions of terms to get millions of digits. But different series will converge on the accurate value for a given number of digits more quickly than others. If we're actually trying to get as many digits as possible, as quickly as possible, we'll want a quickly converging series. A great example of such a modern series for pi is the Ramanujan series. And that is, 1 divided by pi is equal to 2 times the square root of 2 divided by 9,801 times the sum from k equals 0 to infinity of 4k factorial times 1,103 plus 26,930k divided by k factorial to the 4th power times 396 to the 4k power. This series computes a further 8 decimal places of pi with each term in the series. Extremely useful. But back to the earlier question, what is pi doing there? How do these sums, that don't seem to have anything to do with the geometry of circles, spit out pi? Let's just look at that series that adds up to pi over 4. This is known as the Leibniz formula. Pi divided by 4 is the solution to the arctan of 1, a trigonometric function. In calculus, the derivative of arctan of x is 1 divided by 1 plus x squared. 1 divided by 1 plus x squared can also be represented by a power series of the form 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Since this is the derivative of the arctan of x, we can integrate it and get a series that is equivalent to arctan of x. That series is arctan of x is equal to x minus x cubed divided by 3 plus x to the 5th divided by 5 minus x to the 7th divided by 7, and so forth. This is quite useful. Since it's a function, we can plug in different values for x and get the result to whatever accuracy we want by expanding out the series as many terms as we want. To get the Leibniz formula, we plug in 1. So the arctan of 1 is 1 divided by 1 minus 1 divided by 3 plus 1 divided by 5 minus 1 divided by 7 plus 1 divided by 9, and so forth. And we already know that the arctan of 1 is equal to pi divided by 4. So this gives us a way to calculate the value of pi divided by 4, and by just multiplying the result by 4, the value of pi. We can calculate pi as accurately as we want by expanding the series out as many terms as we want to, though in the case of pi, we'll do this with a faster converging series like the Ramanujan series. But I picked the Leibniz series as an example because it's easiest to show why it converges on pi, or specifically pi over 4. You can see a little bit here how different areas of mathematics overlap, geometry relating to trigonometry, calculus, and infinite series. Stephen Strogatz has made the point that infinite series are actually a great way to see the unity of all mathematics. So that's pi. Let's look at some other irrational numbers that can be calculated by series. To calculate e, approximately 2.71828, we can use the following series. 1 divided by 0 factorial plus 1 divided by 1 factorial plus 1 divided by 2 factorial plus 1 divided by 3 factorial plus 1 divided by 4 factorial, and so forth, is equal to e. Or to calculate the natural logarithm of 2, approximately 0.693, we can use the following series. 1 divided by 1 minus 1 divided by 2 plus 1 divided by 3 minus 1 divided by 4, and so forth, equals the natural logarithm of 2. I find these similarly elegant in their simplicity. We're just adding up fractions of integers and converging to irrational numbers. I think that's remarkable. We saw earlier with the arctan function that it's also possible to write a series not only with numbers but with variables, so that the series becomes a function where we can plug in different numbers. There are series for sine and cosine functions in trigonometry. That's good because not all outputs from these functions are nice values that we can figure out using other principles of geometry like the Pythagorean theorem. What are some of these nice values? We'll use radians, where pi divided by 2 radians equals 90 degrees. Sine of 0 equals 0. Sine of pi over 2 equals 1. Sine of pi over 3 equals square root of 3 divided by 2. Sine of pi over 4 equals square root of 2 over 2. And sine of pi over 6 is equal to 1/2. These are angles of special triangles with angles of 45, 30, and 60 degrees, where the ratios of the different side lengths work out to ratios that we can figure out using stuff like the Pythagorean theorem. But these are special cases. If we want to calculate a trigonometric function for other values, we need some other method. Fortunately, there are infinite series for these functions. The infinite series for the sine and cosine functions are sine of x is equal to x minus x to the third divided by 3 factorial plus x to the fifth divided by 5 factorial minus x to the seventh divided by 7 factorial, and so forth. Cosine of x is equal to 1 minus x to the 2 divided by 2 factorial plus x to the 4 divided by 4 factorial minus x to the 6 divided by 6 factorial, and so forth. Again, we have this kind of surprising result where we get trigonometric functions just from the sum of fractions of integers and factorials, which don't seemingly have much to do with each other. Where is this coming from? These trigonometric functions are infinitely differentiable. You can take the derivative of a sine function over and over again, and no matter how many times you do it, the result will be either a sine function or a cosine function. Same for the cosine function. They just keep circling back on themselves when we differentiate them. These series come from their Taylor series representations, or specifically their Maclaurin series representations. I'll describe this using the notation where f prime is the first derivative of a function and f double prime is the second derivative of a function. So using this notation, the Maclaurin series for a function f of x is f of 0 plus f prime of 0 divided by 1 factorial times x plus f double prime of 0 divided by 2 factorial times x squared plus f triple prime of 0 divided by 3 factorial times x cubed, and so forth. What happens if we apply this to sine of x? Let's take repeated derivatives of sine of x. First derivative, cosine of x. Second derivative, negative sine of x. Third derivative, negative cosine of x. Fourth derivative, sine of x. So by the fourth derivative, we're back where we started, and so on. What are the values of these derivatives at 0? sine of 0 equals 0, cosine of 0 equals 1, negative sine of 0 equals 0, negative cosine of 0 equals negative 1. So the terms with the second and fourth derivatives will go to 0 and disappear. The remaining terms will alternate between positive and negative. In the case of sine of x, each term in the resulting series will have x raised to odd integers divided by odd factorials, with alternating signs. The result being sine of x equals x minus x to the third divided by 3 factorial, plus x to the fifth divided by 5 factorial, minus x to the seventh divided by 7 factorial, and so forth. And for cosine of x, it will be similar, but with x raised to even integers divided by even factorials, with alternating signs. The result being cosine of x equals 1 minus x squared divided by 2 factorial, plus x to the fourth divided by 4 factorial, minus x to the sixth divided by 6 factorial, and so forth. Using these series, we can now calculate sine and cosine for any value, not just the special angles of nice triangles. The Maclaurin series also gives an infinite series for another important infinitely differentiable function, the exponential function e to the x. The derivative of e to the x is just itself, e to the x, forever and ever. So in this case, the Maclaurin series is quite simple, no skips or alterations. E to the x equals 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x to the fourth divided by 4 factorial, and so forth. We already saw one solution to this equation where x is set equal to 1, which is simply the number e. These three series for sine of x, cosine of x, and e to the x allow us to see an interesting relation between exponential functions and trigonometric functions. The series for e to the x has all the terms from the series for both sine of x and cosine of x, but in the series for e to the x, all the terms are positive. Is there a way to combine these three? Yes, there is, and it will connect it all to another area of mathematics, complex numbers. Complex numbers include the imaginary number I, which is defined as the square root of negative 1. The number I has the following properties. I squared equals negative 1. I cubed equals negative I to the fourth equals 1. I to the fifth equals I. And the cycle repeats from there. It turns out that if we plug I times x into the series for e to the x, all the positive and negative signs work out to match those of the series for cosine of x and I times sine of x, with the result that e to the power of I times x equals cosine of x plus I times sine of x. To make things really interesting, let's also bring pi into this and substitute pi for x. In that case, cosine of pi equals negative 1 and sine of pi equals 0. So we get the equation e to the power of I times pi plus 1 equals 0. Stephen Strogatz said of this result, quote, "It connects a handful of the most celebrated numbers in mathematics, 0, 1, pi, I, and e. Each symbolizes an entire branch of math, and in that way the equation can be seen as a glorious confluence, a testament to the unity of math. 0 represents nothingness, the void, and yet is not the absence of number. It is the number that makes our whole system of writing numbers possible. Then there's 1, the unit, the beginning, the bedrock of counting and numbers, and by extension, all of elementary school math. Next comes pi, the symbol of circles and perfection, yet with a mysterious dark side, hinting at infinity in the cryptic patterns of its digits, never-ending, inscrutable. There's I, the imaginary number, an icon of algebra, embodying the leaps of creative imagination that allowed number to break the shackles of mere magnitude. And finally, E, the mascot of calculus, a symbol of motion and change." Close quote. He also said, speaking of infinite series generally, quote, "The most compelling reason for learning about infinite series, or so I tell my students, is that they are stunning connectors. They reveal ties between different areas of mathematics, unexpected links between everything that came before. It's only when you get to this part of calculus that the true structure of math, all of math, finally starts to emerge." Close quote. I think we can see that effect in some of the relations between some of my favorite infinite series that I've shared here. Having looked at all this, I'd like to make a couple philosophical observations. One is on the possibility of objectivity in mathematics, mathematical realism, or mathematical Platonism. Infinite series enable us to calculate digits for irrational numbers which have infinite digits. We find the values millions and billions of decimal places out, and we will always be able to keep going. Last I checked, as of 2021, pi had been calculated out to 62.8 trillion digits. What of the next 100 trillion digits, or the next quadrillion digits? Well, I think that they are already there waiting to be calculated, whether we end up ever calculating them or not. And they always have been. Those 62.8 trillion digits that we've calculated so far have been there since the days of the dinosaurs and since the Big Bang. There's a philosophical question of whether mathematical conclusions are discovered or created. You can tell I believe they're discovered, and part of the reason for that is because of these kinds of calculations with infinite series. No matter how deep into infinity you go, there's always more there, and you don't know what's there until you do the calculations. You can't decide for yourself what's there. You have to do the work to find out and get the right answer. Roger Penrose had a similar line of thinking with the infinite structure of the Mandelbrot set. Now, I do think there's a certain degree of human activity in the process, like in deciding what kinds of questions to ask. For example, geometry looks different whether you're working in Euclidean, hyperbolic, or elliptic geometry. Answers depend on assumptions and conditions. I like a line that I heard from Alex Kantorovich. The questions that are being asked are an invention. The answers are a discovery. The other philosophical question is, what does it actually mean to say that an infinite sum equals a certain value or converges to a certain value? We can never actually add up infinite terms. Nevertheless, we can see, and sometimes even prove, where a convergent series is headed. And this is where that concept of limits comes up. I don't know how to answer that question. There are different ways to interpret that. Presently, the way I'm inclined to put it is this. The limits of infinite series are values toward which series tend. They never actually reach them because infinity is not actual, but the tendency of an infinite series is real, such that as you continue to add up more terms in the series, the sum will continue to get closer to the value of convergence.